Welcome. My name is Randy Ellis. In this session, we'll review prerequisite material for nonlinear data analysis. This session will be on linear data analysis. The main concepts for this session are how we can linearly separate data using a hyperplane. This is a form of unsupervised learning, also called clustering. A cluster is simply a set with a centroid. And the k-means algorithm is a common method of finding k such clusters in a set of observations. Machine learning can be broken down in a simple hierarchy. The problem that we'll be looking at is how to divide or partition some data. One hierarchy is that unsupervised learning is a problem of finding natural subsets in the data, and we'll call those clusters. This could be binary, where there are exactly two such subsets that are sought, or it might be multi-class. Supervised learning, we are provided labels that are used to divide the data ahead of time. And again, this comes in a form of binary supervised learning or multi-class supervised learning. A hyperplane is the basic idea that we're going to be using in a lot of our material. So suppose that we have a set of observations. Each one is size n, so there are n real numbers to this observation. We'll define a hyperplane implicitly, and we'll use this block H to denote our hyperplane. So a point V with n, which is a vector with n entries, we'll say it's exactly in the hyperplane means that there's a W vector that's non-zero that we'll use to specify the hyperplane, and we'll use a scalar value B that's just a real number. And we'll say that a point is in the hyperplane means that the dot product with the normal plus the scalar is exactly equal to 0. This is equivalent to saying that the dot product of any vector that's in the hyperplane with the hyperplane normal is exactly minus b. This means that the vector is orthogonal or normal to H. In 2D and 3D, you can think of W as being perpendicular. Sometimes we need a unit normal, n, so what we do is we take our original W and divide it by the magnitude, and that gives us a vector that we'll call n, and then that, of course, will change this value b to a value that we'll call a. Now, how can we use this to partition vectors? Well, suppose we're given any point u, which is a vector with n real entries, and we'll calculate its distance to the hyperplane using orthogonal projection. So suppose that r is some vector that's in the hyperplane. The projection of u in the unit direction is just this. We take u minus this reference point r, and we take the dot product with n, which equals this, and now we can say that this value a is n dot r. So you see that if we're given a reference point r, we can deduce, and a unit normal n, we can deduce the hyperplane scalar a, and that's simply you taking the dot product of the normal and this reference point. So we'll say that a new vector u is on the positive side of the hyperplane if and only if its orthogonal distance to the hyperplane is greater than or equal to 0. Now, this equal is a constant minor annoyance in machine learning, and we're just going to call that the positive side. And then if it's not on the positive side, we'll say that the vector is on the negative side of the hyperplane. So the concept in clustering is, now suppose that we're given some data vector, and we'll define a cluster as a set with members. So we'll denote, for now, we'll denote the set using the index I, and we'll denote the vectors using index j. So a centroid it will denote with the symbol g, and we'll say that this centroid has neighbors, and these neighbors are in the cluster. So how do we define a cluster? Well, one way is we can just say everything is in it, or we can allow subsets. So what we could do is we could say we'll have this cluster and everything that's in the cluster is just in it, or we might say we're going to have subsets and we'll combine those into a bigger cluster. What we'll do is we'll treat the vectors uniformly, and we'll use a distance metric, and in particular we'll use the Euclidean norm from the data vector to the centroid. We'll use that to define the cluster. So that means we're using the L2 norm, the Euclidean norm, or just the ordinary norm, vector norm that you're familiar with. So how can we do this? Well, the idea is we have a centroid, and we can think of this as a mean, but it's not necessarily a mean in the algebraic sense. And we'll write this as the symbol G, as I just commented on. So we can have two options. One is we could define a cluster and then compute the centroid, and we could, for example, simply take the mean. Or we could define a cluster as everything that has a certain squared distance to that centroid. So we can define the cluster, deduce the centroid, or define the centroid, deduce the cluster. And these are in some sense interchangeable, but they are quite distinct. So for example, suppose that we have, here I randomly generated 300 2D vectors, and so there's 100 in each bunch, and you can see visually that it looks like this is one bunch, and then this is one bunch, and then this is one bunch. Well, we can actually do this computationally using an algorithm, and my automatic clustering will do this. Notice that it may not be perfect to your eyes. So for example, it's debatable whether this data point should be in this cluster or this cluster. And numerically it was associated with the cyan colored cluster. You might want it associated with the red colored cluster. So the k-means algorithm is a way of doing this computation. So how many clusters are in a data set? Well, we don't know any automatic guaranteed way to find that. So what we ask is the user specifies the number, and we'll use the symbol k, which is the more or less universally agreed symbol for this. And the problem now is, how do we find k distinct means or centroids in a data set? And there's a heuristic. It's called Lloyd's algorithm, and usually it's referred to as the k-means algorithm. It was one of the earliest ones, and it's a common used, very robust algorithm. So the limitations is that our clusters must be linearly separable. That is, if we have even two clusters, there has to be a way to push a hyperplane between the two of these clusters. And typically the way that we use k-means is, first we'll perform dimensionality reduction. So for example, we might run PCA on a large dimensional data set to get it down to, say, 2D or 3D, and then we will perform our clustering. So the basic algorithm is this, is you can think of the set, a cluster, as having m sub I members and a centroid of g sub I. So you can consider these alternate definitions. Now this alternation is important. We could simply initialize k centroids, and we could do this algorithmically or randomly. It's often done randomly. And then until we converge, what we can do is we can say, if we have two clusters and a data point, we'll associate the data point with the closest centroid, and that will then give us a cluster. And then for that cluster, we can recompute the centroid. And so we can alternate this problem of, here we, from the centroid, compute a cluster, from a cluster, compute a centroid. And if we alternate these two processes, these two definitions, what we'll find is that we'll tend to converge to the k-means clustering. So how can we summarize this session? Well, a cluster is, in the sense, a natural subset of data. We don't know anything except the locations of the data. We'll often use a centroid observation for a cluster. We might use a centroid or mean that is not exactly in the cluster, but typically we'll pick something that's in the data. We'll use some vector norm for distance. The Euclidean is the most common. Others, the L1 or city block norm, is also commonly used. The user has to provide the number of clusters to us, and the k-means algorithm for performing clustering is very widely employed in machine learning.